Welcome back to Calculus 3. I'm Dr. Jeff Groh. Today, we're going to talk about applications. You'll remember the continuity equation. We derived this using the principles of conservation of mass. The only way you can get a change in mass within some region is by flux through the boundary. Conservation laws of which the continuity equation is one, representing conservation of mass, are laws of the form some vector-valued function u and its partial derivative with respect to time, plus the divergence of some matrix-valued function f of u equals 0. If this is a matrix-valued function, we might have Fij, which will depend upon the components of the conserved quantities u. The divergence can be calculated in the following way. The divergence of f will be the sum, as k goes from 1 to n, of d dxi Fij. In this way, you sum out one index and you're left with one index left over. Those will give you the coordinates of the vector that is output. Note that conservation laws are partial differential equations. They seem to require that the conserved quantities are differentiable. The problem is, in many physical situations, the conserved quantities are not even continuous, much less differentiable. There's a phenomenon called a shock wave. A shock wave is a discontinuity in a state variable in a conservation law. For instance, in the continuity equation, the state variable is the density. Let's suppose we're dealing with a one-dimensional problem, in which case the divergence is just the derivative with respect to x, since there is no other variable, and the velocity will be a scalar velocity. Rho could have different values. It could be rho L for x less than 0, and rho R for x greater than 0 at some time. You may have higher density on the left than on the right. With a higher density on the left, you would expect this shockwave boundary at some x0 to move to the right. But what principle governs the motion of the fluid with one density on the left and one density on the right? It turns out the motion of a fluid is completely determined by three principles: conservation of mass, conservation of energy, and conservation of momentum. The conservation laws should be what determines the value of this function, even if it has a discontinuity. But it can't be determined from an equation of this form, because this form requires that the function be differentiable. We need a new formulation of conservation laws that allows for physical shock waves, because shock waves exist. We'll consider the following conservation law: du dt plus ddx of some function of u equals 0. And we'll suppose that in the xt plane we have a shock that starts on the axis at t equals 0 and then moves off along some curve r of t given by x of t t. To try to find a formulation of conservation, which is represented by this equation, we need to find some way of moving derivatives off of these variables that have discontinuities. So here's a plan. Let's multiply this function through by some function phi, and we'll assume that phi is infinitely differentiable. It will be a C infinity function. Also, we're going to integrate. We're going to suppose that phi is 0 outside of this region. This region is called the support of phi. The support of phi. The support of phi is the closure of the set of points on which the function is not 0. So everywhere outside of that region, this function phi will be 0. We're going to integrate in a rectangle that contains the support. It's going to go from a to b, and from t equals 0 to t equals capital T. We'll integrate from a to b, integrate from 0 to t, phi times ut plus f of ux dt dx. If the function is smooth enough to have derivatives, this must be 0. Now, we're going to shift the derivatives off of the state variable using integration by parts. In particular, consider the following integral. Integral from 0 to t of phi du dt dt. We'll set, you'll remember the formula for integration by parts was the integral of u dv is uv minus integral v du. Here though, we already have a u, so we're going to set w to be the thing that we want to differentiate. That's going to be phi, and dv will be everything else. dw will be the derivative of phi with respect to t dt, and v will just be u. We'll have u phi minus integral u phi t will account for the first term of this integral. We'll have u evaluated at t phi evaluated at big T minus u evaluated at 0 phi evaluated at 0 minus the integral from 0 to t of u phi t dt and then dx. We still have to account for the second term. On the second term, the derivative was with respect to x, so we need to perform the integration by parts with respect to the integral on x. We'll have f of u phi evaluated from a to b minus the integral from a to b of f of u phi x dx and then dt. Now you remember the support of phi didn't reach up to t, so the first term on the top will be 0. Also, the support of phi didn't reach either to a or to b, which means that this entire first term is 0. The second term on the top, we have u evaluated at x, and then at t equals 0. That's called the initial data for the state variable u. We're going to call that some arbitrary function of x. Also, suppose that phi of x0 is denoted by phi naught of x. Then we have 0 equals the integral from a to b minus u naught of x phi naught of x dx. The remaining two terms are also minus, but they have both integrals. The integral from a to b and the integral from 0 to t will have u phi t plus f of u phi x dt dx. If we multiply through by a negative, we'll have 0 equals the integral from a to b, u naught of x phi naught of x dx, plus the double integral from a to b from 0 to t, u phi t plus f of u phi x dt dx. If the original function u satisfies the partial differential equation represented by the conservation law, ut plus f of ux equals 0, then it will still satisfy this equation. But there are functions that satisfy this new equation that do not satisfy the old equation. In particular, we no longer have derivatives on the function u. That means u doesn't have to be continuous even anymore. It can have jump discontinuities. It can have shock waves. So this is a more general notion of what it means to solve a conservation law like this. We're going to give it a special name. We call u a weak solution to the conservation law ut plus f of ux equals 0 if for all c infinity phi equation star holds, where we'll call this equation star. I intend to derive the Rankine-Hugoniot jump conditions. First, some notation. Suppose that you have an isolated shock in the state variable u left, u right across some curve. At some point in time, as you approach this position from the left, the state is ul, and on the right, the state is ur. We're going to denote by square bracket u to be u on the right minus u on the left. In other words, square bracket u is the jump in the state variable across the shock. Now, let's suppose that we have an isolated shock wave. Select a point on the shock wave, and on that point, to the left we have state ul, and to the right, state ur. Let's choose a function phi so that the support of phi is within some blob around that point. And what is more, we'll draw a ball around the support. Because the support of phi is away from the initial data, the weak form of conservation will take the form the integral on b of u phi t plus f of u phi x dx dt. Now, the shock curve divides the ball into a left side of the ball and a right side of the ball. We'll break this up into the integral on the left plus the integral on the right of this exact same expression. On each side, u is assumed to be smooth. U will be differentiable on the left it will be differentiable on the right. We have this isolated discontinuity along this curve in the xt plane. That means we can take derivatives of u on each side of the shock wave, just not at the shock wave itself. I want you to consider something about the product rule. The product rule says if I have AB prime, I get A prime B plus AB prime. If I move one term over, that tells me that AB prime is the quantity AB prime minus A prime B. We're going to apply this principle to both terms. On the ball on the left, we'll have U phi t minus ut phi on the left, and f of u phi x minus f of u x phi dx dt. We'll have the same thing on the right. On each side individually, the function u satisfies the original conservation law because it's differentiable on each side individually. The only points in question are along the shock curve. That means these two terms in the first line must add up to 0 because they satisfy the original partial differential equation, the original conservation law. The same is true for these other terms. They also add up to 0. That only leaves a couple terms here. We're going to apply Green's theorem. We're going to apply it on each ball individually. In particular, the first integral will be the integral around the boundary of the ball on the left of minus u phi times dx. The reason there is, when you apply Green's theorem to this term, you take the derivative with respect to t. That will give you a dt wedge dx. In order to reverse the product, to have it in the form dx wedge dt, you need the minus sign. Over here, we're going to have f of u phi dt. When you take the derivative of this term with respect to x, you get a dx wedge dt, which is in the right order, so we don't need a minus on this term. We'll have the same thing for the integral over the ball on the right. It's still minus u phi dx plus f of u phi dt. There is a slight difference. On the left, we evaluate u on the... Because the support of phi on the left does not include the boundary curve, it only includes the curve. And we evaluate then u on the left-hand side. On the ball on the right, we also get 0 on the outer edge on the ball, but on the curve, we're going in the opposite direction, and we're evaluating u on the right. In order to combine these two integrals into one, we need to reverse the orientation on the second integral, so the orientations match. We'll distribute a minus through. When we combine these, we get 0 is the integral on c of the jump in u, phi dx, minus the jump in f of u, phi dt. If we parameterize the shock curve by x of t comma t, then we'll have 0 equals the integral from t naught to t final of the jump in u phi dx dt minus the jump in f of u phi all times dt. Since phi was arbitrary, allowing us to have different supports, we may apply the vanishing integrals principle to deduce that 0 is equal to the jump in u times dx dt minus the jump in f of u. We'll assume that phi is not 0 at the point in question. This then implies if we set s to be the speed of the shock, dx dt, we get s times the jump in u is equal to the jump in f of u at the point of a shock wave. These are called the Rankine-Hugoniot jump conditions. The Rankine-Hugoniot jump conditions tell you something important about the solution. If you have a shock wave, a jump in the state variable must move according to this equation. U is the state variable, f of u is the fluxes, so the speed of the shock will depend upon the state variable and your fluxes. I want to consider a simple traffic flow problem. As long as we are between on and off ramps on a freeway, there should be a conserved number of cars. This is a one-dimensional problem. It is a true traffic flow problem along the freeway. We have the problem that we have two state variables. There's the density and the velocity. We're going to assume an equation of state. This equation of state is that the velocity is some maximum velocity times 1 minus the density over a maximum sustainable density on the freeway. In this way, when rho is 0, the velocity is at the maximum sustainable velocity. As rho approaches rho max, the velocity on the freeway goes to 0. You may have witnessed this yourself. Our traffic flow problem is now governed by the conservation law. 0 equals rho t plus rho v max times 1 minus rho over rho max, x, and still equal to 0. If there should be a sudden disturbance in traffic, let's suppose you slam on your brakes, that will cause a chain reaction that will go backwards through traffic. If there is a shock wave in traffic, a sudden change, it will have to satisfy s times the jump in the conserved quantity rho equals the jump in the fluxes, rho v max, times 1 minus rho over rho max. V max is a constant. It will come out of this jump. We'll have V max times the jump in rho. We can distribute this and get a term rho all by itself. We'll also have minus 1 over rho max times the jump in rho squared when we distribute. What about this jump in rho squared? That should be rho on the right squared minus rho on the left squared, which can be factored as a difference of squares. We'll have s times the jump in rho equals v max times the quantity involving the jump in rho minus 1 over rho max times a jump in rho times rho left plus rho right. We can now divide the jump in rho off. The speed of this shock disturbance is V max times a quantity 1 minus rho r plus rho l divided by rho max. There is something you should notice about this. First, let's take the limit as the difference between rho left and rho right goes to 0. We'll take lambda to be the limit. And the common value then we'll just denote by rho. We'll have V max times the quantity 1 minus twice rho divided by rho max. This is the speed of small disturbances in the limit as the jump goes to 0. You'll recall that our equation of state was that the actual speed of cars on the freeway will be V max times 1 minus rho over rho max. I want you to compare that velocity, the actual speed of cars as they move along the freeway, with the speed of small disturbances. They're quite similar. It's just that we're subtracting more for the speed of small disturbances. That tells us that a disturbance in traffic will move slower than the speed of traffic. It will transfer to you and the people behind you and then the people behind them. It will move backwards in traffic. If you were to suddenly slam on your brakes, that doesn't affect the people in front of you. It affects the people behind you. How fast does a disturbance travel? It depends upon the size of the disturbance. How much you slam on your brakes depends upon the two densities of cars on the left and on the right of that disturbance, how fast it will move back through traffic. There's an equation called the wave equation. Generally, it has the following form. Here, the triangle represents the Laplacian. And so the Laplacian of phi will be the divergence of the gradient of phi. That'll give you d squared phi dx squared plus d squared phi dy squared plus d squared phi dz squared. In one dimensions, the wave equation is 1 over c squared d squared phi dt squared equals d squared phi dx squared. Suppose I have a function evaluated at x minus ct. Whatever the wave profile of that function is, I'm translating it ct units to the right. As time goes by, it'll be more and more translated to the right. By evaluating at x minus ct, it gives me a smooth, constant velocity translation of that wave, whatever it is. I'm going to suppose that my function phi, a function of x and t, is expressible in exactly this form. The derivative of phi with respect to x will be just f prime evaluated at x minus ct. The derivative of the inside function with respect to x is merely 1. Therefore, the second order derivative of phi with respect to x will just be f prime prime at x minus ct. On the other hand, the derivative of phi with respect to t will be f prime at x minus ct times minus c. By the chain rule, you have to multiply by the derivative of the inside with respect to t. That'll give you a factor of minus c. The second order derivative of phi with respect to t then will be f prime prime at x minus ct times c squared. Dividing by c squared, you can see that 1 over c squared d squared phi dt squared is equal to d squared phi dx squared. That means any wave form at all, as long as it's a second order derivative function f, can satisfy the wave equation by simple translation. C will be the speed of the wave. Now, with a little understanding of the wave equation in your minds, I'd like to go back and take another look at Maxwell's laws. Remember what these are. The divergence of the electric field is 1 over epsilon naught times the charge density. The divergence of the magnetic field is 0. The curl of the electric field is minus the time rate of change of the magnetic field. And the curl of the magnetic field is mu naught times epsilon naught times the time rate of change of the electric field plus the electric current. First, before getting into Maxwell's equations too far, I want to look at the curl of a vector field. In particular, let's suppose that f has coordinates f1, f2, f3. We'll get the curl of I, j, k, dx, dy, dz, f1, f2, f3, or the curl of f3y minus f2z. Don't forget a minus on the middle cofactor. Have f3x minus f1z and then f2x minus f1y. Calculating the curl again, here we have f3y minus f2z. We'll have f1z minus f3x and f2x minus f1y. We have then f2xy minus f1yy, and then we subtract f1zz minus minus is plus f3xz. Don't forget a minus on the middle cofactor. We'll have f2xx minus f1xy, and then minus f3yz minus minus makes plus f2zz. And now the last coordinate, f1xz minus f3xx minus f3yy minus minus is plus f2yz. Now, notice the Laplacian of a function phi is phi xx plus phi yy plus phi zz. That's what you get after you take the divergence of the gradient. We almost have that on f1. We're missing the f1 xx. We get what we want. We just have to pay for it. Then the remaining three terms look like a divergence of our vector field and an additional partial derivative with respect to x, we'll be subtracting the Laplacian of f1. Do we get the same thing in the middle term, or something similar? You can see how we have minus f2xx and also minus f2zz. We're missing the minus f2yy, which will help in the middle here a little bit. We end up with minus minus makes plus on the remaining terms. All of them have a derivative with respect to y and end up being a divergence of f minus the Laplacian of f2. In the last coordinate, we have the minus f3xx, and we also have a minus f3yy. What's missing is the minus f3zz. If we add the f3zz and minus f3zz, we end up in that last coordinate having a derivative with respect to z on everything that remains. We get the divergence of f minus the Laplacian of f3. Remember that the gradient of a function is the vector of partial derivatives of that function. What we have here can be expressed as the gradient of the divergence of f minus the Laplacian of the vector field f. We've proved the following lemma. The curl of f is equal to the gradient of the divergence of f minus the Laplacian of f. Now, remember one of Maxwell's laws was the curl of the electric field was minus the time rate of change of the magnetic field. We're going to take the curl on both sides. We can pass the derivative through and get minus the derivative with respect to time of the curl of the magnetic field. The value that we have on the left is the gradient of the divergence of E minus the Laplacian of E. In this case, for Maxwell's laws, we're going to assume that they are source-free. That means we're going to assume that the charge density is identically zero and the current is also zero. That means that we'll have the divergence of E is zero, the divergence of B is zero. The curl of E is minus the derivative of B with respect to t, and the curl of B is mu naught epsilon naught times the derivative of E with respect to t. Since j is 0, there's no additional term. If that's true, if we have divergence E equal to 0 in this special case, the source-free case, this term will go to 0. Also, the curl of B can be replaced. We'll have minus the derivative with respect to time of mu naught epsilon naught times the derivative of the electric field with respect to time. We have a negative on each side of the equations. We'll have the Laplacian of E is equal to mu naught epsilon naught times the second order derivative of E with respect to time. This means that the electric field satisfies the wave equation, where 1 over c squared is mu naught epsilon naught, and c is speed of propagation. By experiment, c turns out to be the speed of light. So we've seen that the electric field satisfies the wave equation. We have source-free Maxwell's laws. What about the magnetic field? We'll take the curl of B, just as we did before. That gives us mu naught epsilon naught times the derivative with respect to t of the curl of E. Now on the left-hand side, you get the gradient of the divergence of B minus the Laplacian of B, just as before. But the divergence of B is, of course, 0. On the right-hand side, the curl of E is minus the derivative with respect to t of the magnetic field. Multiplying both sides by -1, we see that, again, the magnetic field also satisfies the wave equation with exactly the same wave speed as the electric field.